Hi everyone. Okay, welcome to my channel. And today we are going to continue with our linear algebra lessons. And in today's lesson, we are going to look at row operations and elementary matrices. And that's what we are going to try and cover in today's lesson. You see, so far we have seen that linear algebra is all about matrices. It's all about trying to do some operations using matrices. But so far, if you can look at what we have done at this stage, is we have always looked at matrices as objects which one can use to perform different operations. But now at this stage, we are going to actually put that idea way of looking at matrices as object. But now what we're going to do is we are going to start looking at matrices as sets. You see that? And then one thing that we're going to do is we are going to then take as objects the rows or the columns of those matrices. So that's what we are going to be doing from this stage and going so forth. You see that? So which means every time when you picture a matrix, you can picture a matrix as some set such that the different rows of this matrix, they become objects of that matrix. You see that? So which means now what we are looking forward to doing is there a way of actually introducing some operations which make use of the rows of a matrix as objects. So that's what this lesson is going to be about. You see that? So in order for us to be able to put some operations into the rows of matrices, we need some notation that one can use when dealing with matrices. You see that? But in order to get more out of this, let's not just talk about introducing notation only for the rows of a matrix, because the operations that you are going to define, they can also work if one were to perceive the columns of a matrix as objects instead of rows. You see that? So sometimes there will be cases where we can just focus on the columns of those matrices. So what we want now is there some notation that can be used to refer to these two objects that we have now brought forward into our discussion of matrices? You see. So actually, there is some notation that one can use when it comes to the rows. So every time when I want to refer to a particular row of a matrix, I'm going to use the notation Rj. You see that? Where J specifies the row which we are actually concerned with. And when it comes to column, again, we're going to use the notation capital Cj, meaning we are referring to this column number within a matrix, like that. You see, so this is exactly what we are going to do at this point in time. So first we have to introduce this notation, and then after we've understood how this notation works, then it will be time now to start a discussion on the operations that one can do with the rows of a matrix or the columns of a matrix. You see that? So now, with our notation in place, let's move on now to introduce what are known as row operations. You see that? So row operations. So what are row operations? So row operations, just as the name specifies, these are operations that one can perform with the rows of a matrix. And it turns out, actually, there are only three row operations that we have, or we can say there are three flavors of row operations that we have when it comes to matrices. You see that? There are many ways in which one can actually define row operations. It's just that the ones that you will actually look at this case are the ones that are going to actually help us in doing a lot of different processes as far as linear algebra is concerned. You see that? So in linear algebra, one of the goals or that linear algebra tries to achieve is to be able to solve what are known as linear systems. You see that? So you can take the first few chapters of linear algebra as a build-up of the tools that one is going to need for doing some linear algebra processes, which is one of which is just solving a linear system. You see that? So to be able to solve linear system, we'll have to put down some raw operations in place that will allow us to do that. And so far we have 3 flavors of those raw operations that can allow us to do that. And what are those? So the 3 raw operations that we have, one, we have the raw operation Rj plus or minus Ri plus or minus Rj. You see, so there is a raw operation which can be represented this form. So what this raw operation is that it simply adds row I and row j together in a matrix. You see that? So which means there is an operation called addition, which allows us to add together different rows of a matrix like that. You see, so we have this operation represented like this, which switches or which adds 2 rows of a matrix to obtain a new row out of that. Then also we have the operation number 2, which can be represented as alpha Rj, with alpha belonging to some field f. Sometimes this field f can always be equal to the real numbers, but it can be anything. So we have this operation which is represented as alpha Rj. But what does it do? You see that? So what does it do? So this operation, it multiplies row j by alpha. So the second operation that we have is you can multiply a particular row of a matrix by a scalar. You see that? And usually this alpha must not equal to 0 all the time. You see that? So we have an operation of matrices which is called alpha Rj, which multiplies a particular row of a matrix using some number alpha which belongs to some field. So alpha is not necessarily a number, but it's just some scalar which belongs to some field f. We call it a number when the field f is just the real numbers. You see that? So, or sometimes if it's just the complex numbers, but the field f can be anything. You see, so the term field is going to be understood later what we mean by saying something is a field, but the real numbers is a perfect example of what we call a field in mathematics. You see that? So we have this operation which takes a row and multiply it with alpha. Then we have thirdly another row operation which is called Pij. So Pij is an operation which permutes row I and row j. You see, so we have another operation which we can denote as Pij. So Pij is just P stands for permuting. To permute, it means to interchange. You see that? So the third row operation that we have is permute, meaning you can actually swap the positions of 2 rows within a matrix. So these are things that we refer as row operations. You see that? So every time when you perform these, we refer to these as valid row operation. So any row operation that you can define yourself, which works with the rows of a matrix, which is not one of these, we don't term those as valid row operations. We only term those as row operations, the operations that we have agreed on as a mathematics community to say, yeah, this is what we are going to agree as the row operation. Anything which is not this is not allowed to be a row operation. You see that? So every time when we talk about row operation, we'll be talking about one of these 3 flavors of row operations that we have discussed here. You see? So to see now how exactly things work, let's do a few examples to demonstrate how to perform these row operations. You see? So the first row operation that we are going to look at is the example is as follows. So given a matrix A, which is defined as 3, 4, 2, 9, 1, 3, minus 4, 5, and 6, 2, 2, 1. They can say do the following. Do the following. So you can be given this matrix that we have here at the top, and you can be asked to do the following. So the first part is add row 2 to row 3, like that. So you can be asked to add row 2 to row 3, and then B, you can be asked to multiply row 1 by 5 again. Then C is you can be asked also to permute row 2 and row 1. You see, so given a typical matrix, you can be asked to perform all these row operations that we have introduced here. So the question now is, how exactly do things work here? You see that? How do things work here? So what we're going to do now is we are going to give a demonstration as to how exactly can one answer all these 3 different things that have been asked here. So to do that, let's get to it. So solution. So as a solution, we'll consider the matrix that is given to us. We're given the matrix A, which is given as what? So let me copy this 3, 4, 2, 1. And also we're given 1, 3 minus 4, 5. And then the other thing that is given is 6, 2, 2, 1. So we are given 6, 2, 2, 1. Then A, we are asked to find the row operation R row 2 plus row 3. So which means we are being asked to evaluate R2 plus R3. So what is R2 plus R3 equivalent to in this matrix block? So what is the meaning of this? So how we read this is that we should add here to row 2, we must add row 3. You see that? So to row 2, we must add row 3. Or sometimes you can read this as saying add row 2 to row 3. Add row 2 to row 3. Which means row 3 is going to be a fixed row. And then to it, we are going to add row 2 into it. You see that? So which means row 2 will always will remain unchanged. You see that in the process. So which means the first thing here, the convention is that this will remain unchanged. Because how we read this is that to row 3, we must add row 2. So it's add row 2 to row 3. So what is added is going to be added to row 3. So we expect row 3 to be changed after the operation is done. So now what are we going to get in this process? So row 1 obviously is not part of the situation. So it's going to stay as it is. So it's going to stay as 3, 4, 2, 1. And then what we're going to take, even row 2 again is going to remain fixed as 1, 3 minus 4, 5. You see that? Then the next thing that we're going to do now is to this last row, we're going to add to it row 2. So which means I'm going to add things that are in row 2 to things that are in row 3, like that. So first I'll add 6 and 1, which will give me 7. Then I'll add 3 into 2, which will give us 5. Then I'll add negative 4 to 2, which will give us negative 2. Then I'll add 5 to 1, which will give us 6. So this is the result of this row operation, like that. You see. Then B, what else? So B now they are saying we should multiply row 1 by 5. So which means the operation that we are now asked is to find 5 times row 1, which will give us what? So what is 5 times row 1? So it means only the first row in matrix A is going to be affected. The 2 remain unchanged. So we multiply 5 by 3, we get 15. 5 by 4, we get 20. 5, then 1. Then the other rows remain as they are. Like that. You see. Then the next thing that one see is we are asked to permute row 2 and row 1. So which means I have to permute P1, 2. So I have to interchange row 1 and row 2. So what happens is I take row 2 in matrix A and I write it where row 1 is, and I put in row 2 position the row number 2. So I have to switch the position of row 2 and row 1. So it's like swapping these rows together. So when I swap these rows together, what do I get from that? So I will have at the top 1, 3, minus 4, 5, and then at the bottom I'll have 3, 4, 2, 1. Then the other row will remain unchanged as it is. So this is how we actually perform row operations. It's just simple as that. You just have to do as instructed, and then this is how you actually perform them. You see, so I like that the last two rows, they are not confusing in any way. You see that, because they are always straightforward which row is going to be transformed in the process. You see that. But the first one, it can be confusing. Like, who is going to remain fixed? Is it R2 or R3? So sometimes there is this notation that we use to clarify that. You see that. So you have to get used to also using this notation at times. So sometimes you can just write R1 plus R2 to R2. So what this notation means is that you are going to add these two rows together. You see that? And then the result that you are going to obtain is going to be put into row 2. So it means the result goes to row 2 like that. So if you want row 1 to remain fixed in the calculation, you can use this notation like that. So again, if maybe you were to come and write R1 plus R2 and then you write R1, it means our understanding is that the result of this addition will actually go to row 1. So it means now the result goes to row 1. So it means when you add these, whatever you get after the addition is going to be put into the position of row 1, like that. You see. So every time when you want to be clear to the examiner what exactly is going on, you can also make use of this notation, which is kind of like specific as to what exactly, where exactly do you place the result of your addition. So if you're not sure, you can use that. But one thing that you must clarify is always clarify with your lecture what is the convention that is being used in class, because different people, they have their different conventions as to what does Ri plus Rj mean. So always confirm on that and make sure that you follow what the lecture is teaching you. Otherwise, if maybe you are solving linear system, you can actually make use of this notation that we have just introduced here. You see. So yeah, this is some of the things that you have to know when it comes to row operations. Now that we are aware of our row operation, let's move on now to start talking about something which is also quite important, which is attached to this, which are what we know as elementary matrices. You see that? So what are elementary matrices? So to understand what an elementary matrix is, let's put down some notation. You see that? Let's put down some notation. You see that? So let O with an arrow represent any row operation. You see that? So let O represent any row operation. So now O can stand for any of those three operations that we've introduced. You see that? Then one thing that you should understand is that OA means the operation O being performed on matrix A. You see that? So every time when you see this notation whereby we write something as OA like this, it simply means that particular row operation is now being applied on the matrix A like that, because the O with a head, it always stands for an operation. So whenever you see an operation now being written like that, it means now it's operating on that matrix A, which is now input as the argument. You see that? So now, having this kind of information now, it is time now to define what exactly is an elementary matrix. You see that? So we define an elementary matrix which we shall call E as the matrix. So we define an elementary matrix as the matrix E, which we define as OI n. You see that? So what does exactly this thing mean here? What exactly do we mean here? You see that? So an elementary matrix is a matrix that is obtained by performing a row operation on the identity matrix. You see that? So every time when you perform a single row operation on an identity matrix, the new matrix that you obtain is called an elementary matrix, like that. You see? So that's what this last line is trying to say. It's trying to give us a mathematical definition of what exactly is an elementary matrix. It is a matrix that is obtained by performing a row operation onto the identity matrix. So every time when you take an identity matrix and perform a row operation, you obtain what is called an elementary matrix. You see that? So one of the things also that I should add as a comment is this. You see that? So elementary matrices are matrices. So elementary matrices are matrices in which a single row operation has been encoded on them. You see that? So what we are trying to say here is that elementary matrices are not normal matrices. You see that? So these are matrices which are such that they are actually operations. You see that? So it's more like saying it is the representation of a row operation in matrix form. You see that? So the row operations that we have discussed, those three different row operations that we have discussed so far, you have seen that most of the time when we want to command them, we always have to say a statement to say add row 3 to row 4 or add row what to row what. You see that? So having elementary matrices is something which is quite important because it allows us to represent those different types of row operations in the form of matrices. You see that? Which will then allow us now to perform row operations just by making use of matrix operations to perform them, rather than always trying to describe that do this and do that and do that. But you can simply now encode whatever you want to do to a particular matrix onto an identity matrix and then use that identity matrix to what can I say? Then you can use that identity matrix now to the elementary matrix that you have obtained from that identity matrix to actually perform the operation. You see? So that's what elementary matrices are. They are operations in their own right, but they appear in matrix form like that. So yeah, these are some things that you need to know. But now, before we see how actually to create them, let's understand how exactly then can you apply these operations onto matrices. You see that? suppose O is a row operation that has to be applied on some matrix A. You see that? So suppose O is a row operation that we want to apply on some matrix A. Then one thing that you should know is that applying this row operation on matrix A is the same as just finding the product EA on the matrix A. You see that? Where the E that you are seeing is just the operation on the identity matrix. Like that. So which means every time, if you want to perform a particular row operation on matrix A, the best way you can do it is to first create an elementary matrix that stands for that operation, and then you multiply matrix A on the left to perform the operation. So one thing that you must pay attention is to what exactly is going on here. You see? So element matrices must be applied to the left hand side. So every time when you want to apply a row operation, you can first encode that row operation onto matrix A, and then after you have encoded it, you can simply multiply those two matrices together like that. So this is some nice notation that you have to stick to most of the time when you are dealing with matrices. But now let's try and do an example to see exactly what exactly are we trying to say in all this discussion. So to do that, let's consider some practice problems. So example. So the first example one that I would like us to practice is how to actually create elementary matrices. You see that? So the first problem that we're going to ask is create an elementary matrix that adds row 2 and row 3 in matrix A, where A is a 3 by 3 matrix. You see that? So right now what we want is we want to see how exactly can one create an elementary matrix that adds row 2 and row 3 in matrix A, where A is a 3 by 3 matrix, such that A is actually equal to 1, 0, minus 3, 2, 4, 5, 1, 6, 1, like that. So now let's see if we can actually create an elementary matrix that adds row 2 and row 3 in matrix A, where A is a 3 by 3 matrix, you see, such that this A is actually explicitly given like that. So how can we now create this thing? You see. So now to answer this problem, this is how we're going to proceed. So first, we have to recognize what is our operation. You see that? So we see that we want to create an operation that adds row 2 and row 3. So I will say let O be the operation R2 plus R3. So that's what we are going to say. So we'll say let O be the operation adding R2 and R3 together. You see that? So which means now to create an elementary matrix, we have to apply this on an identity matrix. So which means now we're going to call this elementary matrix that we want to create E as E. And how do we get E? We take this operation and apply it on I3, like this, you see. So which means now what I'm supposed to do, I'm supposed to take the identity matrix and then I have to add row 2 and row 3 together. So which means now I have to recall what exactly is I3. So remember, I3 is simply defined as 1, 0, 0, 0, 1, 0, 0, 0, 1, like that. So which means now I have to take these row 2 and row 3 and add them together. So if I take row 2 and row 3 and add them together, what will I obtain at that instant? So if I obtain, what I obtain now at this instant is the first row will remain unchanged as that. And since I'm taking row 3 and adding it into 3, it means row 2 also will remain fixed. Then all the contents of 2 are going to be poured onto 3, so we'll get 0, 1, 1. So which means this is the elementary matrix that stands for that operation. So now let's see if this operation really does what it's supposed to do. So let's take and calculate EA right now. So what is EA? So I'll take E, which is 1, 0, 0, 0, 1, 0, 0, 1, 1, and multiply with A, which is equal to 1, 0, minus 3, 2, 4, 5, 1, 6, 1, and see what I'm going to get here now. So what happens now when I add this? So you see that first I multiply this column and this. So we now know how the multiplication works. So first I'll check this column. Sorry. I'll take this column and I'm going to multiply it with that column and see what I'm getting. So if I take those two together, I'll see that I'll get 1 as my result. Then the next thing, I'll shift to a new row and still keep, I'll shift to a new column on the second and keep my first row. So when I multiply there, I see that I get 0. Then if I do also move to the third and repeat the procedure again, with this one, I see I get minus 3. So I get minus 3 like that. Then now I switch to a new row now. So now I shift to this one and repeat the procedure. So what do I get now? So first this and the first column, I see I get 2. Then this and the second column, I get 4. And this and the last column, I get 5. You see. So now what I have to do now is to take the last part, which is this one, and then multiply with all the columns and see what I get. So with the first column, what do I get? So I have 0 and 1, which is 0. 1 by 2, which is 2. 1 by 1, which is 3. So I get 3 when I sum things up. Then I multiply also with the second. So I have 0 by 0, 0. 1 by 4, 4. 1 by 6, 6. 6 by 4, I get 10. Then I take 0, negative 3, 0. Then 1 by 5, 5. 1 by 1, that when you get 6. So we see that when I multiply E by A, I get that. You see. Now let's check. Let's check something now. So what do we see now? What is the operation O on A? If we apply the operation directly, let's take the matrix A and apply the operation directly. So which means let's take A and multiply and add together row 2 and row 3. So we see that the first 2 rows will remain unchanged. So we'll have 1, 0, minus 3. And also we'll have 2, 4, 5. Then last I have to add the last 2 together. So if I add, you see here, I'll get 3, 10, 6. So I'll see I get my 3, 10, and 6. So you see that doing OA directly and multiplying by E from the A, we still get the same result as hoped for. So we see that we get the same result. So which now actually shows exactly what exactly is an elementary matrix. It is a matrix which exactly encodes within itself a particular row operation, such that every time when you take an element matrix and you multiply from the left with another matrix, it will perform that operation on that particular matrix, as you can see. You see. So that's what elementary matrices are. It's simply something which is obtained by encoding a particular operation onto an identity matrix. And when you have encoded that onto an identity matrix, now you can use that to multiply every time when you want to perform that operation, like that. You see. So this is a nice depiction of what we mean by element matrices. So let's see also more examples. So let's look at another one. So another example will be create an element matrix that swaps row 1 and row 3 of the matrix B, where this B is actually defined as 1, 2, 1, 3, 4, minus 5, 1, 6, 7. You see. So now how can we create an element matrix that swaps row 1 and row 3? So how can we answer this question? So to answer this question, this is how we proceed now. So we'll say let the operation O hat be whatever we're talking about. So it switches row 1 and row 3, so we'll call it P13. Since we're dealing with the 3 by 3 matrix now, we now have to see exactly how this is going to work. So now we'll say let E be the element matrix whereby O has been applied to I3. You see, so which means now I have to apply the operation O to I3, and what will I get? So when I apply my operation O to I3, it means it's going to swap row 1 and row 3. So which means row 3 will go at the top and I'll have 0, 0, 1. Then here I'll have 0, 1, 0. Then 1, 0, 0, like that. So which means now I have this as my element matrix. So now let's see if this thing does what it does. So now let's check. So let's take E and multiply B. So when I take E and multiply B, what do I get? So I have 0, 0, 1, 0, 1, 0, 1, 0, 0 to multiply B, which is 1, 2, 1, 3, 4, minus 5, 1, 6, 7. And let's see what is going to happen from there on. So now we know the procedure. So first we'll check these and that, and then come that, and then come that, and what will you get? So for the first column, we see that we'll get the bottom number, which is 1. For the second, also we get bottom number, which is 6, then 7. Then now we'll come in the middle and take this and multiply all these 3 again. So when I take this and multiply all these 3, I see that the only middle numbers will survive. So I will have 3, 4, minus 5. Then I take the last part, which is this, and multiply everything else. So what do I get? So I see here the first terms only survive, so I get 1, 2, 1. So which gives us exactly what we expect when we switch. So if you look here, if you to switch the row 1 and row 3, this is exactly what you will obtain. So this implies this is the correct elementary matrix. So that's what an elementary matrix is. It is a matrix in which an operation has been encoded on it, and now every time when you apply or you multiply that elementary matrix with another matrix, it always applies that operation onto the rows of that particular matrix. You see. So this is how things work most of the time. This is how things work in most cases. So now the next thing that we want to talk about at this point in time is, now we have seen how to actually create element row operations. But suppose now you want to reverse them. You see that? So how can we reverse them? So now what we want to discuss is what we can call the inverse of elementary matrices. You see that? So how do we obtain inverses of elementary matrices? How do we obtain inverses of elementary matrices? So this is what we want to do now. How to find inverses of elementary matrices. So let's first introduce some notation that we're going to need. You see that? So if E is an elementary matrix that represents the operation O hat. You see that? So if E is an elementary matrix that represents O hat, then we denote as E inverse an elementary matrix that undoes the operation O hat, like that. You see, so every time when you perform a certain operation, an operation in mathematics is something that you can actually undo. You see that? So we don't want to work with operations that when we perform them, we can't reverse backwards. So there are times where we are actually interested in reverting back to where we came from. So in order to do that, we introduce now what are known as inverse elementary matrices. So inverse elementary matrices are just matrices that oppose or reverse the operation that you did before. So if you performed some operation O, which might have been represented in terms of matrices as the elementary matrix E, then you can actually create another matrix which undoes that operation, which we denote as E inverse or E to negative 1, like that. You see, so E to negative 1 is just an operation which undoes an operation. But the question now is, how exactly does one obtain such operations or the inverse operations? So to do that, this is what we're gonna see. You see that? So we're gonna now write down some ideas on how exactly to find these inverse element operations. You see, so let's look at them one at a time. So let E be the elementary matrix that stands for the operation O hat, such that O hat is an operation which takes alpha of Ri and adds it to Rj. You see that? So let E be an operation. Let E be the elementary matrix that stands for the operation O, such that O is defined as follows. O takes a multiple of rho I and adds it to rho j. You see that? So the first flavor of the row operations that we have discussed is actually defined more generally this way. It is the addition of a multiple of another row onto another row. You see that? So this is the correct definition of the first element row operation. It means it has to involve taking a multiple of one row and adding it to another row. So now E is a matrix that stands for that. The question now is, how can we then find the inverse operation? You see that? Then E inverse is defined to be such that, so E inverse is defined to be such that it represents the operation O bar head. So what I'm going to do now is every time when E stands for operation O, the inverse will represent the operation for which the inverse stands for as O bar, like that, with a head to mean operation. So if E is an elementary matrix that represents that O, then E inverse is an elementary matrix which is defined such that it represents the following operation. It represents the operation Rj minus Ri, like that. You see. So it represents the operation Rj minus Ri, which means from row J, subtract alpha Ri, like that. So this thing that we have written here, it reads, so this part, so it reads from row J, subtract alpha times row I. So this is how we read this statement. So it means you'll be performing this thing on row J, whereby from row J you will subtract alpha row I. So this is how you obtain the inverse operation of this addition row matrix or row operation. So in order to practice what's going on here, let's look at a few examples. You see, because it can be tricky when things are just written this abstract. So a typical example will be as follows. You see that. So suppose E is an element matrix suppose E is an elementary matrix that adds two times row 3 to row 1 in A, where A is a 3 by 3 matrix. You see that? So suppose E is an element matrix that adds 2 times row 3 to row 1 in A, where A is a 3 by 3 matrix. Do you see that? So what we're going to ask now is write down E and E inverse. You see that? So write down E and E inverse. That's what you want to determine now. How can you find these two matrices? One which adds 2 times row 3 to row 1 and one which reverses that operation. You see? So let's see how one can answer this kind of question. So to answer this kind of question, this is how we proceed. At first, you must always have the element matrix E itself. You see that? So what I'm going to do is I'll say let O bar be the operation 2 times row 3 plus row 1. So which means O is the operation that takes 2 times of row 3 and adds it to row 1. So this implies now what is E. So it means it is this operation done on to I3. You see, because we're talking about 3 by 3 matrices, but this generalizes to any square matrix. So it works like that. So which means now I have to apply this row operation onto I3. So remember, let's recall what is our I3. So remember this I3, it is simply the matrix 1 0 0 0 1 0 0 0 1. So which means now what does happen? So we see now that I have to take 2 times of row 3 and then add that to row 1. So I see that if I were to do that, I'll get 1 0 2 like this, and then the other things will remain the same as 0 1 0 0 0 1. So this is what I get, which means this is actually the element matrix that represents that operation. Now, how can we obtain the inverse? You see that? How do you find the inverse operation? So every time when we want to find the inverse operation, what we have to do is that the first operation was involving a certain multiple of a row being added onto another. You see that? So which means if I'm to invert backwards, I have to remove what I've added to row 1. So it means from row 1, I must remove 2 times of R3. So I must create now an operation which removes what I added before. You see, so row 1, he had nothing, but I added 2 times of row 3, which means E inverse must remove that thing that has been added before. So it is defined this way. So how can we create this E1? So let's create it. So it means from row 1, I'm going to subtract 2 times of row 3. So 1 will subtract 2 times 0, which is 1. 0 will subtract 2 times 0, which is 0. And then 0 will subtract 2 times 1, which is negative 2. And then everything else will remain as it is. So we see now that this is our E and E inverse. So every time when you're given a particular element matrix E, which adds a certain multiple of another row onto another row, then you can simply obtain the inverse by removing what you've just added onto that row. Then you get the elementary matrices that you need. So if you can check close, you will see that here there's been changes now. You can see that in the original matrix, that 2 was a positive. Now this 2 is a negative. So this is one thing that I'll have to highlight. So not the sign change. So pay attention to that sign change, which is happening there. So this is what you should know when it comes to element matrices so far. But let's look also on how to invert some other operations as well. So the second thing that we want to look at is suppose let E be an element matrix that represents so let E be an element matrix that represents the operation O such that O is the operation alpha Rj, which means O now in this case stands for multiplying some row j with some alpha. You see that? So we'll assume that this alpha is not equal to 0 at this instant. You see, so let's assume that E is an elementary matrix that stands for that. You see that? Then E will be a matrix that represents the operation O bar head such that O bar head is simple 1 over alpha Rj. Like that. You see. So those are things that you should know. That every time when you multiply by a particular row by a certain number, then if you want to undo the process, you just have to divide throughout. So this is how you can actually find E and E inverse if you know this property. That the operation that E will stand for will be the one that undoes what you have been done. So since what you did was multiplying by something, to undo the process, you have to divide by what you multiplied with. So that's what this thing is trying to say here. So to practice it, let's look also at examples. So a particular example will be as follows. Given that E is a matrix that multiplies row 4 by 6. So let E be a matrix that multiplies. So let's call it an E matrix to mean element matrix. So let's given that E is an element matrix that multiplies row 4 by 6 in some 4 by 4 matrix A. Determine both E and E inverse. You see. So now we have an E, which is an element matrix that represents that particular operation. Now, how can you find both E and E inverse? So to answer this problem, this is how we proceed now. So at first, we'll define an operation O. And we know that operation O is an operation which takes row 4 and multiplied by 6. So which means it's just represented as 6R4, like that. You see. So this implies now to get E, I'll say let E be the elementary matrix which takes this operation and applies it to I4. So now let's recall what we mean by I4 at this instant. So now I4 will be the matrix defined as 1 0 0 0 1 0 0 0 0 1 0 0 0 0 1, like that. So which means now what I have to do, I have to apply this operation onto I4. So what will I obtain now? So I can see now that the E will become as follows. So what I'm going to do, I'm going to take row 4 and I'm going to multiply by 6. So if I take row 4 and multiply by 6, I'll get 1 0 0 0 0 1 0 0 0 0 0 sorry 0 0 1 0, then 0 0 0 6. So this is the operation that actually takes row 4 and multiplies it by 6. So now how can you find E inverse? You see that? So we now know that in this case to find E inverse, we know that O bar is going to be given by 1 over 6 by R4. You see that? So that's how do I find E inverse? So E inverse will apply O bar onto I4, which means instead of multiplying by 6, in this case now we're going to divide the identity matrix in the 4th row by 6. So we'll get 1 0 0 0 0 1 0 0 0 0 1 0, then 0 0 0 1 over 6. So this gives us our two matrices that we're looking for, the E and its E inverse, like that. You see, so that's it. That's it. So those are things that you should know. What about permutations? What about permutations? So how do we deal with permutations? You see that? So if E is an element matrix such that, so if E is an element matrix such that E is equivalent to Pij, then what you should know is that E inverse will be just Pji. You see, so if E is an elementary matrix that permutes row I and row j, then E inverse will be one that actually returns them back like that. You see, so it will be one that just returns them back. But remember, this has to be applied onto some identity matrix where Pij is an operation which switches, and then P inverse will be one which actually replaces back j and I like that. So if you switch back j and I, then you will see that that's what it does. But one thing that you are going to observe all the time is that when you're dealing with this kind of transformation, E inverse will always turn out actually to be In, because when you take a matrix that you have actually done something onto it, then if you return it back to mate, you will see that it will go back to the identity matrix, because when you apply Pij onto In, it will transform this into a new elementary matrix. So when you want to find the inverse, then the inverse is simple. So one way to write it nicely is to just say the inverse is defined as taking the reverse operation onto E. So when you take the reverse operation onto E, then you get In out of that. So this is the whole subject of elementary matrices. That's what they are. So every operation that you want to do, you do it on your identity matrix, and the undoing one will be the one that does the opposite thing. You see? So it will be the one that does the opposite thing most of the time. So yeah, that's all that we can say for now with the elementary matrices. So just as we have said, this section was to try and build tools that we're going to need to assist us in solving linear system. So we are going to see one role that can be played by these elementary matrices when it comes to the solution of linear system. So for now, let's just practice what we have just seen here. Otherwise, thank you guys for watching. So if you find these videos helpful, it would be nice also to hear your comments or suggestions in my channel. And yeah, thanks guys for watching. See you next time.